According to what we know. We'll come up here and put a clock on this right here. That's supposed to be an AND gate. An AND gate. So what would we expect on the output? Instead of putting a clock on here, let's just put a 1 up here and see what we should expect on that. This would give me 0, this will give me a 1, this would be 0, this would give me a 1, that would give me a 0. What would I expect on that? We expect a 0, right? You understand? Huh? It takes all highs to equal a high on the output. I've got an odd number of inverters. If I've got an odd number of inverters, it means it will always be opposite on the input. Not necessarily 0, it will always be opposite. Right? You understand? So when my clock goes high, this will be low. When my clock goes low, according to that, that'll be high. So according to what we know, if I put an odd number of inverters in there, the output of an AND gate will always be low. Because we can never have what? We never can have all high. What are we ignoring? We're ignoring the propagation delay of all of those inverters. So right now, if I switch this to a 1, okay, so let's come up here and look at this. Let's start off with a 0. So if this right here was a 0, then this would be a 0 right there. That would be a 1. That'd be a 0. That'd be a 1. That'd be a 0. And that would be a 1. So the output would be what? A 1. According to what we know. Oh, I'm sorry. It would be low. You're right. Sorry. So this will be low. Okay. So what's going to happen when this right here goes to a, let me clear this out, erase, clear this out. What's going to happen when this goes to a 1? Okay, now look, so right now this is a 1, right? You understand? Okay. Watch. So this guy goes to a 1. This is a 1, that's a 1. 10 nanoseconds later, this goes to a 0. 10 nanoseconds later, this goes to a 1. 10 nanoseconds later, this goes to a 0. 10 nanoseconds later, this goes to a 1. 10 nanoseconds later, this goes to a 0. So what we do is we get a little pulse out of this thing because it's got to propagate through the gates, right? You understand? But when did it do it? Well, it's going to do it every time this has one of these. We're going to get a little pulse out of this. But only on the rising edge. On the low end, once this switches to a 0, and this goes to a 0, right? You understand? We're not going to get anything right there, even though it takes time to propagate through the gate. It had a 1 right here, but this goes to a 0 instantly. So this circuit is what we call an edge detector. This circuit, if I'm on a time, so we know what's the difference between synchronous and asynchronous data transfer. Synchronous is time with a clock. Asynchronous is untimed, right? So if I'm using a clock, what would I want to time on? Would I want to time on a high, or would I want to time on a low, or would I want to time on an edge? Why? Because there's no timing on a high, right? You understand? Okay. So what we want to do, if we're dealing with synchronous data transfer, we need to come up with some type of circuit that detects an edge. So this is what we call an edge detector. This scope does, oh my goodness, this scope does a fairly good job of it. It's not a really good scope. But on which edge? On the rising edge. Right? So we have the circuit set up here on the board. Okay, we're using the 7408, which is a 2-input AND gate, quad 2-input AND gate. And then we're using the 7400, which is a hex inverter. And I have this exact circuit wired up. So this is the rising edge, and look what I get out of the gate. Only on the watt. Yeah, we'll come over and look at the falling edge if I can get this trigger. Now it's hard to see right there, guys. Let's see if I can get it stuck down.
Ow.
No, it's not gone. It's just the scope can't see it. What I'm gonna do is just switch the trigger over to the falling edge. The scope is so fast that the scope can't see it, right? You understand that, but it's there. So we'll come over here on our trigger and we'll trigger on the falling edge. Notice we don't see the watt. We don't see the pulse. We take the trigger, switch it over to the rising edge, and then the triggers. Not a problem, trigger, guys. Like that. The trigger on it. Let's put a trigger on it. No, we don't want a trigger on that. Oh, I know. I had a trigger on both of them. So it's getting very confused. So there's pulse, right? And I switch it over to trigger on the falling edge. We don't see the pulse down there. If I change this out and put an OR gate on that, an OR gate would detect the falling edge, and an AND gate detects the rising edge. So now we've got a circuit that does what? That only looks at an edge. These are edge detectors. And we'll get into later on into some more complex integrated circuits. So if you come over here and you see a symbol, and you see this triangle like that, this means it's edge triggered. Or edge timed, but we call it edge triggered because that triggers the circuit to operate. So this guy here would look for a rising edge. If I'd have put a bubble right there, then it would look for a what? Falling edge. And so later on, we're going to get into synchronous counters. We're going to get into JK flip-flops, and all these guys are going to be what we call edge triggers. So they're going to be synchronized with a what? With a clock. The book uses 3, but the problem is that we don't have any test equipment. I thought the 100 megahertz scope should be able to catch it, but for some reason, when you get up into the real high frequency, with real high settings on that scope, it goes out of trigger. So this is only a 25 megahertz scope, so that's why we're only seeing the scope is what's not having a time to respond to the little pulse that's coming on there, because it's only there for, you know, a couple of nanoseconds. So edge detection circuits, guys, these things are really cool. They'll be built into the circuit though, and so if we see a symbol and it's got that triangle right there, it means it's what? Edge trigger. If it don't have the bubble, it means it's edge triggered on the rising edge. If it does have that the bubble, it means it's edge triggered on the falling edge. Are we okay? Any questions on that?
So with the bubble on the falling edge, triangle, rising.
No, the triangle means it's edge trigger. If we draw the triangle without the bubble, it means it's on the rising edge. If we draw the triangle with the bubble, it means it's on the falling edge. So that don't mean, this don't mean rising edge. This means what? Edge trigger. Just in general, right? A big question. Any more? So according to our Boolean algebra formulas, and this is what equations, when we try to reduce circuits, it says a and with a 0 will always be a 0. But here when we use the inverters, that doesn't take into account the propagation delay of how long it takes to propagate through those inverters, right? Okay? All right, guys, let's go to lab.